Hey guys, so we still need to fill, we started this yesterday. So quick refresher, we learned how to write domain and range. It needs to be in numerical order, no repeats. And we learned what functions were. They are relationships that are very specific and they have x's that don't repeat. We filled in just about everything except for this bottom. We didn't fill in the domain and range on a graph, and we didn't fill in this equation bubble. So we're going to do that first, and then we'll do the back of it. So for this graph, the domain is the x values that it covers. So you need to think real quick to yourself, what direction does the x-axis go? And the x-axis goes left to right. And so I'm a visual person. I need to see things. So on the x-axis from left to right, the circle stops here and it starts over here. So from left to right, these are the x values in this direction. Oh, I better use a different color for you. Whoop. Here we go. This direction. That doesn't look much different, does it? Okay, so this value, if I look at my graph, this is where my y-axis is right here. If I count backwards, it's -1, -2, -3, -4. So it starts over here at -4, and then this spot right here is +1. Okay, so let me get rid of these. So my x's go from -4 to +1. Now this is really tricky because you need to realize that we're not just dealing with single points anymore. This circle is what we call a continuous circle. There are no jumps in drawing this circle. I don't have to pick my pen or pencil up the entire time I draw it. And so what that means is that we need to cover every single x value along the way. And that's usually where kids get a little confused because the domain and range look different now. So in our other domains and ranges, we were just writing down the single numbers that were involved. But now we need to include everything in between it. And that's literally impossible to list out. You can't do that. You can't write down every single decimal that it covers. And so we have a shortcut way of being able to do that. So what we do is from left to right, it covers from -4 to 1. So we put -4 over on the left side, and we put 1 on the right side, just like it kind of looks on the graph, right? -4 is on the left and 1 is on the right. And we use less than or equal to or greater than or equal to symbols to say that it covers everything in between. So x is kind of in the middle of these two numbers because it includes these two numbers. And it falls on 4 and it falls on 1, so we're going to use the equal to symbols. And then you draw your brackets around it just like you did for your set notation before. So the way we read this is the domain covers -4 to 1. If they were to ask you, well, how do you write that? Like, what's the notation for that? You would say -4 is less than or equal to x, which is less than or equal to 1. So the domain covers everything from -4 to 1. That's what this is saying. Okay, so let's do the range, and the concept is the same for the range, except now we're looking at y values. So you're going to look at the top of your graph to the bottom of your graph. Okay, and so the circle goes, this is 3. The top of the circle is at 3, 1, 2, 3. And the bottom of the circle is at -2. Let me pull these out of the way for you. So the top of your circle is at 3 and the bottom of your circle is at 2. Now, you have to put them in numerical order, just like we did with the other ones where we had just single numbers. It still needs to be in numerical order. So I'm going to write -2 first, because that's the smaller number, and 3 goes over here. But the range is dealing with y values, so you're going to put a y in the middle now. And does it hit -2? Yes, so put the equal to symbol on it. And does it hit +3? Yes, so put the equal to symbol on it. So again, how to read this, the range covers -2 to +3. Or you could say that the notation for it is -2 is less than or equal to y, which is less than or equal to 3. So y covers everything from -2 to 3. in my range. Because this circle was continuous, I was able to draw it all the way from +3 to -2. I didn't have to pick up my pencil at all. Weird notation, I know, that's new to you. You haven't seen something like that before, so don't get freaked out about it. It's just our way of saying that X is everything in between and Y is everything in between. That's why we put the X in the middle and the Y in the middle, because it's everything in between. Okay, so the equation bubble now. In order to figure out the equations, we need to figure out what X and Y could be. And I think that the easiest way for this is for you to think to yourself, is there any X that I'm not allowed to plug in? So, is there any X that I can't plug in? Is there a reason I can't plug that X in? Is something weird going on that, like, if I plug in 0, oh my God, the world's gonna explode? And the answer is no. There's nothing that would prevent me from substituting any number into this equation. I can use any negative number that I wanted. I could square it and -1 from it. I could plug in any positive number that I wanted. I could square it and -1 from it. I could plug in any fraction I wanted to. I could plug in any decimal I wanted to, positive or negatively also. So there's really nothing that I can't plug into this equation. And so to write that domain, the fact that I could plug anything that I want to, we have a shortcut for that, and it's called all real numbers. So the shortcut is saying there's nothing that this can't be. The domain can be anything. The X values can be anything that we could possibly think of to plug into this equation. There's nothing stopping us from choosing a number, fraction, decimal, positive, negative, nothing. Anything goes. The range, on the other hand, is a different story, because now we're saying, well, if I plug in anything, what could I potentially get out of this thing? So the best way to kind of test that out in my mind is to create a little table for myself to see, like, you know, is there any weird patterns that I notice going on? And so my go-to is to plug in -2, -1, 0, 1, and 2, because that kind of gives you a good range of numbers to decide, oh, I've got some negatives going on, I've got a weird 0 going on, and then I've got some positives. So if there's anything funky happening with this equation, I would notice it, hopefully, because you've covered just about everything. Negatives, zeros, and positives. Fractions and decimals are another story. So I always start from the bottom because those are the positive numbers, and I like to deal with the positives first. So the equation is x squared minus 1. So 2 squared minus 1 is 4 minus 1, which is 3. That seems pretty normal. That's a normal number. I'm going to do the same thing with 1. So 1 squared minus 1. 1 squared is 1 minus 1, again, is 0. That's no big deal. 0 is an okay number to deal with. If I plug 0 in, I get 0 squared minus 1. So this becomes 0 minus 1, which is -1. -1 squared. Now be careful here, because this means -1 squared with the parentheses around it. So you're including the negative when you write your square. -1 times -1 is +1 minus the one that's there, which is 0. Hey, I already had 0. Okay, so something funky is going to happen with this equation. I need to figure it out. And then -2 squared minus 1. -2 times -2 is +4. Minus 1 is 3. I already had a 3 also. So what kind of happened was, as I look down this row, I have 3, 0, -1, 0, and 3. So 3 went down to -1 and came back up to 3. So if I were to keep going, like if I looked at more negatives, if I continued this pattern up, and then if I continued the positives down, what I would see is that my positive number and my negative number result in the same thing. So -2 gave me 3, and +2 also gave me 3. -1 gave me 0, and +1 also gave me 0. And I would see that continually. If I plugged in +5 and -5, I would get the same answer out. If I plugged in 10 and -10, I'd get the same answer out. If I plugged in 1,000,000 and -1,000,000, I would get the same answer out. So what this is telling me is that there's a stopping point to this, and this is the key stopping point. So that -1 is really important because that's the smallest number I could get out of this thing. But what I'm noticing is that my numbers could keep going up and up and up, and then these numbers can continue to keep going up and up and up, but they're going up at the same rate, which is kind of important to us. So to write my range for that, the whole point of that was to write the range, by the way. -1 is the smallest number, but there's no limit to my biggest number. And when I don't have a limit, I need to represent that somehow. And that means I need to start including infinities in my answers. So -1 is the small number, and positive infinity is the big number. And my range deals with y's. Did I actually get -1 out? Yes, so I'm going to use my equal to symbol. But here's the weird thing. You can't ever reach infinity. So you're not allowed to put the equal to sign on this symbol because you can never equal infinity. There's always something bigger than the number that you just thought of. So no equal to's ever on infinity symbols. Never, ever, ever. Throw your squiggles around this thing. Okay, so now we need to decide if this is a function or not. None of my x's repeated. My y's repeated, which is okay, remember, but none of my x's repeated. So yes, this is a function. Most of the equations, like 95% of the equations that we deal with this year are going to be functions. Actually, you know what? Closer to 99% of the equations we deal with this year are going to be functions. So don't really worry about it. If you see an equation, at this point, just assume that it's a function. Okay? All right, so the back of your paper, we're going to write down what it looks like as pairs. Oh, I better plug this thing in. I'm going to go dead real quick. Hold on. We're going to write down what pairs would look like if they were a function, and then what they would look like if they weren't a function. Because I think sometimes it helps us to understand what a function is if we know what it doesn't look like. So what it looks like as a function for pairs, or coordinates. You can use the word coordinates here. What it would look like is a list of coordinates. Whoops, that's an ugly parentheses. 7, 9. I'm just going to make some stuff up. -5, 0. The fact that I have no x's repeating means that it's a function. Okay? And then for the not function part, all I have to do is make one of my x's repeat. So that's what I'm going to do. I'm going to use the same coordinates, but I'm going to throw one in there that maybe uses 3 again, but now it's using a different y value. See how it's using a different y? 3, 4, and 3, 2. X equals 3 repeats. And that's the reason it's not a function. I've got this 3 going on twice. No good. Tables. So on the other side, we had an XY table. So if it is a function in this column here, in the X column, I'm not going to see any numbers that are the same. I could see all my Y's being the same. Look at that. Isn't that weird? X is 2, 3, 4, and 5, but Y is 10 all the way down. That's perfectly acceptable. X's didn't repeat, so no X's repeat. Okay? That's okay. Here's a function that is not. So actually, I'm just going to reverse this on you. I'm going to put 10s all the way down here and put different Y's here. But because these X's repeat, it's not a function anymore. for mappings, we talked about this yesterday. In fact, we actually gave an example of a not function yesterday, but let's do another one. So this mapping, remember this is your x bubble, and the second bubble is your y bubble. So let's just do 2 and 3 and -1 and -5. I'm just making stuff up. So 3 goes to -1 and 2 goes to -5. Looks great. There's only one arrow from each x. So one arrow from the x's. What it would look like as not a function then is that I would have a double arrow coming off of one of my x's. So let's do 2 and 3, and we're going to do -1, -5, and 0. Let's throw in another number. So let's say I've got 2 to -5 like before, and I've got 3 to -1 like before, but now all of a sudden 3 also goes to 0. So that double arrow nonsense that I got going on there, that's our issue. Double arrow on 3. No good. That means that I've got the point 3, -1, and 3, 0. 3 is repeated. No, not okay. The graph, we're going to use the vertical line test on this thing. We drew a couple of graphs yesterday, so let me draw another one for you. Doesn't hurt to have more examples. So we have these things, these graphs in algebra called stair steps, which are, they're fun. They're a fun graph. So if I go up this way, oops, sorry, that should be like diagonal-ish. Oops. I love these ones. They're so fun. Kind of looks like a stair step, but they're sideways. It's not like straight up. They're like diagonal stairs. So if I tested this using the vertical line test, and let me use a different color to test it in. If I vertical line tested this, doesn't matter where I hit this thing, it's only going to hit once. So it passes the vertical line test. Okay, and then one that doesn't work, let me just draw a triangle. How about that? Let's draw, boop, boop, boop. See, I got a triangle going on here. If I vertical line tested this triangle, it hits here and it hits here. Or if I tested it somewhere else, it's there and it hits there. If I tested it right on the corner, it looks like it passes, but because it doesn't pass somewhere else, automatically fails the vertical line test. Remember, it only has to fail once. Doesn't matter how many times it passes. It fails once, it's done. Okay, and for equations, just about any equation you have will work. So let's say I've got the equation y equals 3x plus 1. No matter what, I can plug anything I want to for x, and whenever I plug in, I'm going to get one y value out. So this passes. If I made a table of values, say I plugged in -1, I'd get 3 times -1, which is -3, plus 1 is -2. If I plugged in 0, I'd get 1. If I plugged in 1, I'd get 4. So notice that none of my x's are repeating, right? So this is good. Here's a weird one. You ready for this? This is weird. Say I had 3x equals y squared. 3x equals y squared. This is weird, right? Okay, so we actually need to think backwards on this one. Whenever I see a square on my y, I want to think backwards. So let me plug in -1. -1 times -1 is +1. And then I'd have to divide it by 3 to get x out. So this is 1/3. But if I plug in +1, So I have to think backwards again. I'm actually using my output to determine my input, which is backwards thinking. If I plug in 1 and I square it, I get positive 1 divided by 3. It's still 1/3. So see how if I plugged in 1/3 in both cases, I would get the same, I would get 2 different y values out. That's no good. So it doesn't work. Let's write down that we can create different outputs. For one input, okay? So your job now is to go do your exit ticket and get that turned in. So I gave this to you yesterday. You're going to create the table, pairs, graph, and mapping for each equation. So this is your equation. You create whatever values you want. I would suggest that you pick small values because you're going to have to go graph them over here. And our graph only goes from -6 to 6. So I would pick numbers for your x that are between -6 and 6 to plug in. You can create any 4 you want to. Then you're going to list them as coordinates or as pairs. You're going to show me the mapping. So you'll make an X bubble and a Y bubble, and you'll use these numbers from your table in your bubbles and draw your arrows to how they go. And then you're going to graph these points on your graph for both of these. Okay? And then make sure you get that turned in. If you have any questions, ask Mr. G and he will text me, and I will hopefully be able to get back to you rather quickly. All right, guys, be good.